Guys, I've been told just as I was coming into this lecture theatre that yesterday's lecture video is not on Vula. As far as I'm aware, did everything, but something must have gone wrong in the upload and I didn't realize. So I'll redo it in third period and when I do this lectures video. So I apologize about that, I was not aware. Okay, let's carry on with curvature. So I'm going to write here curvature. And today we're going to get on to something called osculating planes. Okay. Okay, so I introduced curvature yesterday. We did a sort of a paragraph or so of writing about it. Curvature is the measure of how fast the direction of the curve changes. Okay, or at least that's its definition. In a sort of a gut feel sort of way, it's how tight the curves are. How tight the curves are. Nice gentle curves or really tight curves so that if you were driving you'd have to really watch out and make sure you didn't go off the side of the road. Okay, so that's what curvature is. It's defined as how fast the direction of the curve changes. So here is how we work it out. A little bit of overlap with yesterday's notes. We have our tangent vector r dash of t. And what we're going to do is we're going to strip the magnitude from that. We're not interested in the magnitude of the direction vector. We're interested in its direction. So we're going to turn it into a unit vector. So we have the unit tangent vector, which we call t of t. I always find this a slightly confusing notation because there's no dash. That big T has no dash. And yet it is related to the derivative of r. So I do find it slightly confusing notation, but that is its conventional name, the unit tangent vector big T. And it's the r dash vector divided by its magnitude to turn it into a unit vector. So we're not interested in whether it's if a little particle is moving along the curve, we're not interested in is the particle moving fast or is it moving slow. We're just interested in its direction. Okay. And then we define curvature just looking at my notes. Yeah, okay. Curvature is defined. Now curvature, it's the Greek letter kappa. It looks like a capital letter K except small like a lowercase letter. Okay, kappa. And it's defined as the modulus of the rate of change of big T with respect to arc length. So in a sense, for a given arc length is the unit tangent vector. So if you have a very gentle curve along your space, a very gentle bend in your space curve, and then later on you have a very tight bend in your space curve, a key difference in those two curves would be that over the same distance the one bend has a small change in direction, but the other bend has a big change in direction for the same actual distance. So kappa, the curvature, is defined as the rate of change of the unit tangent vector, which really just encapsulates the directionality of the tangent, with respect to arc length. Okay, now it's all very well defining curvature that way, but it's not actually, if I said, okay, go forth now, I'm going to give you a curve, work out kappa at t equals 10. How would you do it? It's not actually a very useful formula to work with, even if it's a nice theoretical definition. So, of course, because r is a function of t, r dash will be a function of t, big T will therefore be a function of t, so how now can we differentiate it with respect to s? Well, s being the arc length, what we could do is we could reparametrize our curve with respect to arc length, because then we'd have s throughout rather than t throughout. But reparametrizing with respect to arc length is actually The example I did was a very easy one, but that was because I deliberately chose it. Usually it's quite a pain. Of course, usually big T is in terms of T, not S. We can reparameterize the curve with respect to arc length, RWT with respect to arc length. But that is frequently, I'm just going to write here quite messy. Yeah, it's fundamentally what it is. It's quite messy. It ends up being quite hard labor to do that frequently. However, we can work with T as a function of the parameter T using the chain rule. Okay? So the chain rule says okay, so that's the chain rule. Chain rule says that d big T by d little t is d big T by ds times by ds by dt. Okay? So kappa, which is defined as the modulus of the first factor on the right, is equal to the modulus of the thing on the left divided by that. Okay, that's a little bit more tractable. That's a little bit more usable, because the numerator of that fraction on the far right there is the derivative of big T with respect to little t, and that's fine because big T is a function of little t, so you just do the derivative. And at the bottom we have the modulus of r dash. And that's fine, and that's perfectly doable. It can, however, be a huge mess. Because if you think about it, we started with r. Okay, so r could be some fairly ordinary vector function. Then we differentiate. Okay, fine, there's the potential for a little bit of mess there. What if there was product rule involved, a quotient rule? But okay, r dash. And then to get big T, we had to turn r dash into a unit vector, which means we had to divide by its modulus. Its modulus is necessarily going to involve the square root of the sum of the squares of the components. So big T can sometimes be quite a clunky vector to work with. And now we're still going to differentiate it. So each term in big T has the potential of being some massive quotient with a square root in the denominator. And now we're going to come along and differentiate it. So it's going to be quotient rule in all directions and fractional powers and all sorts of stuff. So it's not really a hard thing to do, but you often end up with quite big, messy terms. Yes?
Are you saying that the derivative of r with respect to t is ds by dt?
ds by dt is the modulus of r dash. If you go back to where we did the reparametrizing in terms of the arc length function, remember s is, just want to write it exactly as I wrote it in my notes. There we go. We had s of t is defined as the integral from a to t of the modulus of r dash of u du, from which it follows that ds by dt is the modulus of r dash of, well, t in this case. We no longer need the dummy variable. Remember? And in fact, possibly most of you don't. We spoke about integration and differentiation as being inverse processes of one another. If s is the integral of mod r dash, then mod r dash is the derivative of s. So we're taking advantage of that. Okay, so if we put in another few lines of manipulating the algebra, which I'm not going to do, further algebra can simplify this expression to, make sure I get it right now. Where do I have it written? Where do I have it written? There we go. Kappa equals the modulus r dash of t crossed with r double dash of t over r dash of t cubed. Okay, I'm not going to do that work. I think it's in your textbook, I'm not sure. But so kappa is defined as that thing over there, the modulus of dt by ds. That's what it's defined as. Some fairly easy manipulation using the chain rule can take you to that, which at least is doable, whereas the dt by ds is not easy to work with. But this thing over here is fairly pedestrian to work with, but it can leave you with a rather, or can, on the way to the answer, can pass through some seriously messy territory. A little bit of extra work which I am omitting. If you want to do it yourself, you can leave some lines blank and maybe go find proof online or in your textbook. But a little bit of extra algebra can simplify it further to that thing at the bottom there. And that expression at the bottom there is really easy to work with. Much easier than anything involving big T. Yeah, is there anything else I want to say before doing an example? I don't think so. Just we'll check my little notes here. Don't want to leave anything out. Oh right, radius of curvature, absolutely. There is one more thing. And there's also sort of a third thing. Now, I'm going to show you another formula for kappa that we are not actually interested in this course. However, you will encounter other courses where you might be interested in it, so I wanted to be here in your notes for completeness sake. It's in your handbook in exercise 51. And I'll put it in a slightly different color here. In the special case, which we are not interested in, but you should always keep your maths notes. Never throw your maths notes out. Keep them. Keep them forever. Like literally forever. In the special case, you never know when you're going to need them for some funny reason. I've used my first year notes. I had to, a couple of years ago, I had to teach something called complex mapping. And I hadn't actually taught it as a lecturer before, but I'd done it in first year. So I went and dug out my first year notes and went through all my notes on complex mapping, which weren't great notes, but they were good enough. I managed to make much better notes than when I actually taught it. And that was 2 or 3 years ago. So you never know when you're going to need those first year notes for something funny. So in the special case, where the curve, that should say curve, is 2D in the xy plane, we can work with that formula for kappa that's in exercise 51 of your handbook. So I'll write it here. But other than that one little homework problem which I've given you for practice, and it's not assigned as a TUT question, it's just a homework problem. Other than that just little homework problem, we won't see it again. Let me get my brackets in the right place. That should be a square over there, and then that's a 3/2. In this particular course, we're interested in 3D stuff. We're interested in space curves. But you might encounter a 2D curve on the xy plane in some other course, and you have to do something to do with curvature, and then you can use that formula. They're equivalent formulas. They're absolutely equivalent formulas. Simply a special case. Okay. And then radius of curvature. So The radius of curvature, your textbook uses the symbol rho, which is just trifle unfortunate, seeing as we already use rho in two other contexts. We use rho in spherical coordinates, but also we're going to be doing quite a lot with density, and rho is a frequent symbol used for density. But your textbook does use rho, so I will also use rho. The radius of curvature is 1 over kappa. So big kappa means small rho, and small kappa means big rho. And what the heck is rho in this case? Well, if you have a curve, let me try and draw a curve that has a nice gentle bend and then has a nice tight bend, okay? Let's say that's your curve. Imagine, I'm going to have a point over here and I'm going to have a point over here. Imagine that you want to have a circle that's snuggling up against that curve and has those two dots, well, two circles that have those two dots as their points of tangency. Another way of thinking about it, imagine you've got a bubble and you're blowing the bubble and you want the bubble to be as big as possible, but just snugged up against that curve. Your radius of curvature is basically the radius of that circle. Okay, one is a big radius, one is a small radius. Big rho, small rho. Small kappa, big kappa. Rho large, kappa small. Other way around, rho small, kappa large. Because kappa is measuring your curvature, is measuring how tight the bend is. Very tight, big kappa. Kappa is a measure of the tightness of the bend. But the tighter the bend, the smaller the circle you can tuck in there, and hence the smaller the radius of curvature. Okay, I'm tucking in the circle. That is non-technical language. You will not find that in a textbook. And radius of curvature, I wouldn't be surprised if you find quite a useful measure in some course somewhere along the line. Okay, alrighty then. Now I'll jump into an example. And which example will that be? Number 48. Find the curvature of the twisted cubic. Look, it's our old friend, the twisted cubic. T squared, t cubed at a general point, so just some random t, so the curvature will still have a t in it, but also at 0, 0, 0. So we're going to be finding two different kappas, one full of t's and one a specific number. And then it also asks what's the radius of curvature. Okay, cool. So let's work it out using the best of all three formulas, which is this one over here. This is the best one to use. That one with the r's in it. Oh dear, sorry, big jump there. So kappa equals the modulus r dash of t crossed with r double dash of t over the modulus of r dash of t all cubed. So let's work out r dash of t. It's 1, 2t, 3t squared. Let's work out r double dash. It's 0 and 2 and 6t. We are going to want to cross them. Okay, so we need to do a cross product. Okay, do a cross product whichever way makes your heart happy. There's different ways of doing cross products. I still do my cross products the way my physics lecturer taught me in first year back when I was new to vector geometry. What's that? That is 12t squared minus 6t squared, and that is 0 minus 6t, and that is 2 minus 0. So my cross product is 6t squared minus 6t and 2. Okay, I did that quite fast. Did I do it right? Anybody see a mistake? Mistakes are always possible. I'm agreeing with my notes, and that is always comforting. And this will be the modulus of 1, 2t, 3t squared all cubed. Okay, all right. Well, let's do that. What is that? The modulus of a vector is the square root of the sum of the squares of its components. 36, come stylus, catch up with me please. 36t to the 4 plus 36t squared plus 4 over square root of 1 plus 4t squared plus 9t to the 4, and that's all cubed. And now I don't think that won't simplify. That won't simplify. I've got to leave it just like it is. And that's the answer to the first part. They say, what is the curvature at a general point? That's the curvature at a general point. In fact, if we wanted to be nice and tidy about it, we could write kappa of t. Okay? But then we will also ask, what's the curvature at the origin? So first of all, because k is a function of t and r is a function of t, not a function of a point, but of a function of a parameter value at a point, we need to know what's the value of t that corresponds to the origin, and of course that's just t equal to 0. Some people I know are not quite sure where I'm getting these from. What I'm doing is I'm asking myself, what t value do I need to plug into r in order to get that point? In this case, it was pretty obvious. It was 0. Sometimes it's not so obvious. You need to do a little bit of thinking. And so basically the question is asking us what is kappa at 0? Square root of 4 over square root of 1 cubed. That's 2. Now I'm right at the bottom of my page here. If I press the arrow one more time, I'll jump onto a new page. So I'm just going to write the radius of curvature alongside rather than underneath. Okay, so if I drew the curve at the origin, I'd be able to snuggle in a circle of radius half of whatever units are being used. So probably quite a small circle, really. 2 is quite a large kappa. Ooh, excuse me. Yeah?
Is there any more concrete definition of the radius of curvature in terms of how much of the curve is accommodating that we want to snuggle into?
Well, you're not really accommodating anything except a point.
Okay.
Mathematically speaking, only the point is being held in common between the circle and the curve.
Okay.
Yeah. Even though at a sort of a gross diagrammatic level, it might appear that there's more. Okay, curvature. It's really not very hard. You're just using a formula. So again, if you go and look at old tests and exams, you'll frequently see that question 1 has A, B, C, D, whatever, and one of those little things is often calculate the curvature at such and such a point, and it'll be maybe 3 marks. This is one of those little things that's often one little thing in a long string of things that you need to do in a bigger problem. So why don't you give it a go and do number 49? I'll come back up here. I'm just going to write here, you try 49, and then I'll scroll back up so you can see my method. One thing is that the problem that I just demonstrated, the question asked for a general point, kappa at a general point, so that's why I worked out kappa of t. But usually you just asked for kappa at a... No, 49 also wants general point. 49 also wants general point. But often you're asked for kappa at a particular point, in which case I would say plug in your t value, t equals 0 or whatever. There's R dash at the top of the screen. There's R double dash. If I had only been interested in kappa at 0, I wouldn't have worked out this thing on the left here. I would have plugged in t equals 0 straight after working out R dash and R double dash, and my cross product wouldn't have involved any t's. It would only have involved numbers. I wouldn't have bothered with that if I hadn't been interested in a general point. However, exercise 49 also general, so off you go. All right, we're heading on to osculating planes now. Osculating planes and normal planes and tangent planes. but osculating planes is the main one. Okay. So r dash of t, could you please keep quiet, is the direction of the tangent. Or it's an arrow that points along the tangent. Let's put it that way. Okay, it's your velocity, but velocity vector, magnitude and direction, okay? T of t, the unit tangent vector, is r dash of t turned into a unit vector. I'm going to do a picture shortly, but first I'm introducing the vectors I'm going to put into that picture. Could you please keep quiet? Even if you're talking about mathematics, could you please keep quiet? Okay, here's a nice little fun thing. Because T of t, big T, sorry I'm leaving out some arrows, here we go, has constant magnitude. So big T is a unit vector. Big T is a unit vector. R dash is almost certainly not. As our little particle speeds up and slows down along the curve, as our velocity increases and decreases in magnitude, the R dash arrow will sometimes be short and sometimes be long. But big T will always be an arrow 1 unit in length. So because big T has constant magnitude, T dash is orthogonal to it. Which is something I gave to you without proof earlier. I said R dash will be orthogonal of a vector's derivative will be orthogonal to it if the original vector is constant in magnitude. Which I wrote in terms of R, but here it is in terms of T. Okay. If we scale T dash of t into a unit vector, because just because t is unit in length doesn't necessarily mean its derivative is. So you take the derivative of t, you turn it into a unit vector. We get another vector that is that kind of has its own name, just like big T has its own name of unit tangent vector. We have something called the unit normal vector. Which, just like we got the unit tangent vector, we take t dash and we divide it by its magnitude, turn into a unit vector. And then, and once again, I'm giving this to you so that you have complete notes, but you'll probably never see this word again in this course, but maybe you'll see it elsewhere. If we cross big T and big N, we get a vector called big B, which is called the binormal vector. And because big T is unit and big N is unit, when you cross two vectors, think of your definition of the cross product back from first year. If you have A crossed with B, the magnitude of A cross B is mod A mod B sine theta, if you remember. So, but because big T and big N are orthogonal to one another, the theta between them is 90 degrees, and sine of 90 degrees is 1. The magnitude of big T is 1, the magnitude of big N is 1, so the magnitude of their cross product is 1. So the binormal vector, we know for sure, will also be a unit vector. You know what, I should speak to some of my friends who do computer graphics. Wouldn't be surprised if these vectors come in useful in computer graphics. I'm just guessing. I'm not actually sure. Because what happens is that big T, big N, and big B form an orthogonal set of axes of unit vectors. And that's quite a powerful thing. That's quite a powerful thing, because if you think about it, in our 3D space, where we generally divide it in rectangular coordinates with an x, a y, a z coordinate, and we have our I vector, our j vector, and our k vector along our axes, we can describe any point in space as a linear combination of those 3 unit vectors. So by taking some random curve somewhere, picking a point, and saying here at this point we are imposing a coordinate system onto this point where our elementary unit vectors are not I, j, k, but are t, n, and b, you can then define all space in terms of a point on a curve. And it's really a very powerful thing. In this particular course, we are very interested in the geometry of the system, and we're not so interested in the actual vectors of big T, big N, and big B. But still, that system of big T, big N, and big B, giving you an orthogonal coordinate system defined by 3 orthogonal unit vectors, it's very powerful geometry. Okay, having given that, what I'm going to do now is I'm going to draw a picture. So in order to have space to draw a nice picture, I'm scrolling away from the text a bit. Here we go. I'm going to have a curve. Okay, there we go. Some curve. In fact, let's make it a little bit more interesting than this. There we go. There's a curve. All right. And let's take a point on that curve. Let's have a look. Let's take a slightly bendy point. Let's go over there. Okay. If I have a particle, and that particle is it's that red particle over there, and it's traveling along the curve, then I don't know where the origin is. The origin is somewhere in space, and R will be a vector pointing from the origin to that red dot. And R is an important vector because it describes where in space that point is. But R is not that useful a vector for talking about the actual shape of the curve. R dash would be a better vector for talking about the actual shape of the curve, because we know R dash is tangent to my curve. So here's R dash. Okay. Big T, I'm going to draw next to R dash. Big T has the same direction as R dash, but it's unit in length. Okay, T dash will be orthogonal to T, and if we scale T dash into a unit vector, we get N. Here's N. Okay. R double dash, I would like to draw. R double dash, we'd need to know some more information. I can draw R dash simply by looking at the picture of that black squiggle. R dash is either pointing exactly where I've drawn it, or it is pointing 180 degrees the other direction, but we know R dash is tangent to the curve. R double dash is the acceleration of our particle. I don't know whether our particle is speeding up or slowing down, but let me just, for the sake of the diagram, put R double dash in here. Let's say my particle is slowing down slightly. R double dash is pointing slightly backwards from the direction of motion. Okay, R dash and T and N we can draw onto that picture. We don't have a lot of choice where we draw them. R double dash, just for the sake of a diagram, I could have drawn anywhere. I need more info for accurate. R double dash. Okay, sorry, my dashes are quite close together. I'm going to redraw them. Okay, and the binormal vector is pointing out of the page. Okay, cool. So T and N and binormal and pictures and squiggles and red arrows, but I gave a heading of osculating plane, and that word osculating doesn't seem to have come up yet. So what's going on? Let's have a look. I've got black in the picture. I've got red in the picture. How about some blue? Do you think blue will be nice and visible? Okay, what we're going to do is we are going to now impose some planes onto this picture. Could you please keep quiet? This is very important. We are going to impose some planes. There's the actual plane that the curve is drawn on. Now, of course, a space curve itself generally does not exist on a plane. It squiggles all through space. That particular picture I've drawn, of course, is on a plane. It's flat on my screen. It's flat on your page. The osculating plane is the plane that, if you take a curve and you take a dot on that curve and you look at a little piece of the curve around the dot, the osculating plane is the plane that piece of curve, you can picture that piece of curve lying on. So if you took a piece of cardboard and your curve was a piece of wire in space and you were interested in one little dot on that wire, if you took a piece of cardboard and you put it up against the curve and you said, okay, little piece of curve, you're lying on my piece of cardboard, that piece of cardboard is your osculating plane. It's the plane that is the best fit plane to contain a piece of curve around your point. I think an easier way of remembering how to get your osculating plane is with this picture. Because in this picture, we have a special case of a curve. We have a curve that's actually flat on the page. The osculating plane is the page. And if we want the equation of the page as a plane, well, whenever you want to find the equation of a plane, the most important thing you're looking for is its normal. And if you look at that picture, those red arrows are all lying on the plane. If we want the normal to the plane, we can cross any two of them. Well, except for r dash and t, because they're parallel. So if you take r dash and r double dash and cross them, you'll get a vector pointing out of the page. And that will be the normal to the plane that is your page. Okay, so the osculating plane is the page, if your plane is drawn flat on the page. Okay, so the osculating plane. Let's give a slightly more formal definition. The osculating plane, where's a nice definition here? Oh, that's blue. I don't want blue right now. I want maroon. Osculating plane. In the context of that orthogonal, that set of orthogonal unit vectors that I've described with n and t and b, the osculating plane is the plane determined by t and n. It is the plane that comes closest to containing the part of the curve that should say curve near your point of interest, wherever it is that you're doing your calculations. Okay, its normal is r dash crossed with r double dash, or t crossed with m. But because we're not really interested in the magnitude of the normal to our page, just doing r dash times r double dash is good enough for our purposes. In our picture, the osculating plane, sorry, that's written a bit funnily, is the page. Okay, all right, but then we also have the normal plane. The normal plane is normal to the curve. It's orthogonal. It chops right through the curve. Yeah, question, but I don't have a lot of time. Yes?
So is this the normal different to our big B vector?
No, it'll be parallel to big B.
Okay. But we want the magnitude to be...
Oh, we couldn't care less about the magnitude because we're just trying to find the equation of the plane. there might be contexts where the magnitude of your normal to the plane is important, but not the context we'll be using it in, which is just to find the plane equation. So you can go to a whole lot of hard labor to find big B, but for our purposes it's not necessary. Okay, so I drew that blue dotted line now onto the picture. That blue dotted line is where the normal plane goes. The normal plane chops right through your page where that blue dotted line is. Doesn't look that blue on the screen, does it? Anyway, over here it's blue. Quite a light blue, actually. Interesting. Okay, so I'm going to do a little bit of writing. So I'm scrolling down. The normal plane. Normal plane, osculating plane. It's the plane determined by B and N. Okay. It consists of all lines orthogonal to T. In our picture, it cuts, I'm just doing a perpendicular sign there, it cuts orthogonally through the page at, and I'm going to write here at the blue dotted line, but you know, if yours isn't blue, don't write blue, write something meaningful, at the blue dotted line. Okay, that's the normal plane. And then you also get the tangent plane, but the tangent plane would be the one defined by B and T, and in our picture it would be orthogonal. It would also cut through the page, but orthogonal to the blue dotted line. There's some very nice pictures online. If you just go into Google Image and put in I don't know what would find you the best pictures. If you actually put in something like binormal vector, normal vector, or osculating plane or something into Google Image, you can find some really, really great pictures that are beyond my ability to just draw by hand. And it gives you a really good idea of what's going on. How just like our X, Y, and Z axes divide our entire world into octants, into basically big blocks divided by our coordinate axes. T and N and B divide the whole world into big blocks that are in the context of your actual space curve. Okay, let's stop there.